We said the features that we're interested in here, in this model, are, first of all, we would like to be able to go in and say something about what the bond length is. How much distance do we have between the nuclei in our diatomic molecule? We would also like to know, when this goes into vibration, how much amplitude of vibration do we have? So again, we're thinking of amplitude of vibration around the center of mass. So there's a center of mass somewhere between the two nuclei. And the vibrations are going to take place on either side with respect to the center of mass. And then the spring, right? So we said what happens in molecules is as the nuclei approach each other, the electrons can't collapse, right? The electrons are not able to collapse and continue to stabilize that interaction. So as the protons do move together, we do get increases in potential energy. Okay. And we represent that with a spring. And we say it's like it has a force constant of K. So those are the things that we'd like to be able to go in and figure out here. We'd like to work in terms of bond length, stiffness of the bond, amplitude of vibration in my diatomic molecule. We said this is related to rotation and vibration. And on Tuesday we went through and sort of derived, I guess we did derive, rotational energy states. I don't know how you guys felt about this, but this was a big shock to me. This idea that when you're looking at rotational energies, they're quantized. And it traces back to angular momentum. So for the rotational quantum states, we said here is an energy of rotation. And the formula came out as L plus 1, h bar squared, reduced mass times bond length. Let me write down the reduced mass here. Here's all the fine print that goes along with that formula. So I have to know what the reduced mass is referring to, and then I have to know what values there are for L. What are the values for L? This is angular momentum. Right, so I can have integer values. And there's no n here to limit how high the angular momentum could go, so we could have higher and higher states of rotational kinetic energy. All right, we had started looking at vibrational energies. Vibrational quantum states has a little different feel to it. What we said was, if we take, I'm going to switch back and think of this as a potential energy, I think. There's always a little complication here because some of this potential energy effect that we define, and the book uses potential energy, I'm going to go with their convention. It does include some kinetic energies of the electrons also. So anyway, I'm not going to worry about that, I guess. I'm going to call it potential energy. And it says that in our diatomic, if the nuclei start to get really close to each other and the electrons can't collapse along with the protons, then we're going to start to get repulsions, and that's why that potential energy is going really high for short distances. What's R here? And we're going to say this is the internuclear distance. Now there's an equilibrium value for that. Where's the equilibrium on here? Yeah, exactly. I've had a roller coaster going back and forth here. Equilibrium would be right there. So this is really the bond length here. Is what's the internuclear distance at equilibrium? All right. And then we said that this is the bond energy. At equilibrium. we said we could model this as a parabola. So what we wanted to do was take this relatively complicated function and say, you know, we're really interested in, if we're looking at vibrational quantum states, are we interested in enough energy that it would take the molecule completely apart? And you go, no, I'm not looking at taking the molecule apart. I'm looking for states where the molecule stays attached together. And those would correspond to regions down in here. Okay, so they're going to be quantum states down in this potential energy region. And we're going to approximate that with a parabola. And the energies that we get here, energy as a function of R is equal to, I'm going to say, minus the bond energy plus 1/2 K R minus R naught squared, and I can think of that as X. So back when we defined springs, we said there's kind of a natural length of the spring, right? If it stretches out, then the X begins to increase. But at the natural length, X would be equal to 0. And what that's getting replaced with is the equilibrium separation. So if I got two nuclei at the equilibrium separation, what's the X value? 0. You know, it's like having a spring at its natural length. If the distance between the nuclei increases or decreases relative to R naught, that's what's going to contribute to X. So we're going to say X we can get by taking R minus R naught, finding out what that difference is. All right. And that gives us a parabola. And you guys remember this at all from chapter 38? We looked at this briefly. They called it the simple harmonic oscillator. It was one of the homework problems. Yeah. So we had a potential energy that looked like a parabola. And we actually solved for the wave function for the lowest possible state. But what would the wave functions look like? What would be the wave function for the ground state? So I'm going to label these. I'm going to say this is vibrational state 0. This is vibrational state 1. This is vibrational state 2. We'll get a series of states. Vibrational state 0 is going to look like, yeah, it's going to look like peaks in the middle, and then we're going to have exponential drop-offs when we're outside into the region where we don't really have enough energy that we should be there. And what would V equals 1 state look like? Yeah, I'm going to get peaks on either side here. So if I look at that symmetry going right down through the center of this potential energy curve, I'm going to get functions that are even, and I'm going to get one that's odd. I'll get another one that's even, get another one that's odd as we make our way up. In any case, these are the wave functions that correspond to vibrational quantum states inside molecules. So what does that mean? To take a wave function that is, wave function is a function of internuclear separation. And well, we can do the probability argument, right? How would I turn this into a probability? Yeah, I square it, right? I can square this and turn it into a probability. Where am I going to get most of the probability? Kind of the central region. And what that's saying is, if I go in and take a look at this molecule, what's the most likely separation between the two protons, or between the two nuclei? And you go, yeah, the most likely separation would be the equilibrium separation. And then as I move away from equilibrium in either direction, those are going to become less and less likely. What happens when we go into state number 1, the first excited state? If I look at probabilities here, where the probability is going to show up? On the sides, right? So in this state, how likely is it to find the two nuclei separated by their bond length? It's 0, right? It's the probabilities are to find it a little more than the bond length, or a little less, but the bond length itself probability actually drops to 0. So this is weird. Okay. So instead of just having nuclei that oscillate back and forth, following some kind of a trajectory, what we have is a probability distribution. This is if I interact with this molecule, there's a probability that the protons would be separated by their bond length. There's a probability there would be higher than the bond length, probability less than the bond length, and the different wave functions are telling us what those probabilities look like. Okay.
So why again can't it be at the bond length probability?
Because the wave function would go to 0 right there. So if I took, these are wave functions that we're looking at. If I square the wave function will give me what?
Probability.
The probability density. So that's my probability density. If I start squaring these, what I'm going to find is, in the ground state, the two nuclei spend most of their time pretty close to equilibrium separation. But if I move up to the next state, I'm going to get a peak here and a peak here. And it says there's actually no probability of being right at the equilibrium separation. Yeah, and we've seen this before. We saw this with hydrogen, right? Why is it in a p state, right? A p state would be what? Angular momentum is 1, right? So in a p state, there's going to be a node right down through the middle of the atom where there's no probability of the electron being there. It can be on this side or this side, but there's no probability down the middle. So it's the same kind of idea here. It can be a little larger than equilibrium separation, it can be a little less, but there's actually no probability at all of being right at equilibrium. Yeah. For v equals 1, exactly. So this is behaving kind of like an S state, this is behaving kind of like a P state in that sense.
So
here we have nodes right in the central regions, yeah.
So it's not like a spring because a spring
Not like a spring.
It would want to come back to equilibrium, at least for a little bit.
Let's think about this. So if you had a spring, let's say you just get a spring out, a mechanical spring, and you attach a couple objects to it and let it oscillate back and forth. Where does it spend most of its time? Right at equilibrium, larger than equilibrium, or shorter than equilibrium?
On the edges, on the outside?
We actually don't spend much time at equilibrium because if you had a spring, it's going the fastest right as it goes through its equilibrium. So, you know, the classical version is more like this. If I had a spring that was just oscillating back and forth and I took a series of photos just randomly, it's more likely I would pick it up away from its equilibrium than someplace close. Because that's when it slows down, right? It slows down out here and then it picks up speed and goes fast in the middle. So, yeah.
So does it like teleport from side to side?
Yeah. No, you know, there's different ways to interpret this.
Okay.
But the bottom line is, if we go in and we interact these molecules with something, if we fire something at them, or what this is telling us is, when we do interact with it, how will the nuclei be separated at that time? So if you want to call it teleportation, teleportation kind of implies that we still have a well-defined trajectory, right? I think most people would agree that in quantum physics, we're not really thinking of the particles going from one place to the other. It's not like, how can it get from here to here? It's like, if I interact with this, there's a probability of interacting here and a probability of interacting here, without ever being in between. All right, the formulas we get when we solve all this, and we did this back as a homework problem for the lowest state, for the ground state, the energy that we get for vibration turns out to be V plus a half h bar omega, where omega is equal to k over mu to the half. And V is our quantum number. And V can be 0, 1, 2, 3, 4, 5. So it's kind of interesting to look at the comparison between the rotational states and the vibrational states for these diatomics. Now, it's also important, I guess, to say we can extend this. It doesn't have to be diatomics, but it gets really complicated really fast, right? If we have more than 2 nuclei, then we end up with multiple rotational axes that we have to consider, and multiple vibrational modes. So we're just going to look at diatomics. That's going to be enough for us. So let's map these out. Let's say here is energy is equal to 0. Is it possible to have 0 vibrational energy in my diatomic molecule? What's the least amount of energy I can have? 1/2 h bar omega. So that says that I'm going to have my first state here at V is equal to 0 would have energy of my 0 state 1/2 h bar omega. And I guess we have to, I want to talk about omega a little bit. Omega suggests that there is some kind of oscillation, there's some kind of motion going on, but here we're just using omega to keep track of the spring, the stiffness, the bond stiffness divided by the reduced mass. That's something we did back in 4A. So we're really not thinking, again, as something really literally following some frequency. We're just saying that there's a certain amount of energy and it's proportional to the bond stiffness and the reduced mass of the system. But we do use omega just as kind of a convenience, but it can be misleading. All right, how much energy would I have in my V equals 1 state? Yeah, that'd be 3/2, right? So the energy of this state would be 3/2 h bar omega. If we have a molecule that shifts from state 1 into state 0, what happens with that leftover energy? Yeah, we'll generate a photon. So we'll have a photon that comes out of here. What will the photon energy be determined by? Yeah, E1 minus E naught, right? So what we can do is take the difference. And how am I going to come up with these energies? Yeah, from the vibrational formulas. Okay, so on problems, homework, midterm, very important. First of all, identify what kind of problem we're looking at. Am I looking at a rotational problem? Are they asking about rotational energies? Are they asking about vibrational? Are they asking about hydrogen atoms? Because depending on which system we're looking at, the quantum numbers, the energies are going to be very different. Okay? And next down midterms, if it's a question about vibrational states and you're putting in infinite potential well wave functions, it kind of looks like I'm not sure what you're doing. Okay, so the first thing to make sure is that list all the different sorts of quantum states that we've looked at, and make sure you're clear on what applies where. Okay, is my advice. So for this, the energy of the photon is going to work out to be what? Well, I could think of this as E1 minus E naught. That's going to give me h bar omega. So I can go back and say that the energy of the photon is going to depend on what? It's going to depend on the bond stiffness, and it's going to depend on the reduced mass. Okay. So again, it's properties of the molecule. Right? I can go in and say, what are these properties for this molecule, and figure out what the photon energies will be. What's V equals 2 state? Where is that going to show up? Yeah, so the energy here is going to come out as 5/2 h bar omega. I hope. Did we get that right? 2.5. Yeah. So V plus 1/2. And how much spacing do we have between here and here? Oh, it's the same, yeah. So this is h bar omega. This is h bar omega. Now, can I jump from state 2 down to state 0? Because we did that with the hydrogen atoms, right? Turns out with vibration and rotation, that's very uncommon. Okay, with vibration and rotation, we take it one step at a time. We don't skip steps. And there's a reason for that. It's cheating, that's right, it's cheating. No, it's not it. So, but that could be, it's a good guess. So it has to do with angular momentum. Okay, so if we look at differences in angular momentum for these states, particularly the rotational states, the rotational states change by 1 unit of angular momentum. Well, angular momentum's got to be conserved. How much angular momentum can a photon carry off with it? It can only carry off 1 unit at a time. Okay? And that ends up saying that for rotational transitions, you just jump by 1 step. Very unusual to jump by 2. It involves some kind of a 2-photon process. All right, let's look at some numbers for vibration in, what do we look at for rotation? Carbon monoxide? Is that it?
Yeah.
Okay, so let's do some more carbon monoxide studies here. So here's carbon monoxide, and let me go back and write some stuff down for rotation. When we did the study with carbon monoxide, what we found was the energy of the, I gotta say rotation. Rotation for rotational states, going from L equals 0, transitioning between L equals 0 and L equals 1. The energies of the photons here worked out to be 4.76 10 to the minus 4 eV. This is photon energy. And that corresponded to a wavelength of 2.61 millimeters. That's the wavelength of the photon that's being generated there. And from that, we were able to show that the bond length was equal to 113 picometers. So that was all kind of interesting. What we want to do is compare some of these numbers with vibration. So, what do you think? Is the spacing, the energy spacing in vibration, is that going to be bigger in magnitude, or is it going to be less, or about the same as rotational energy states?
Less.
Yeah, vibrations tend to be a lot bigger. Okay, rotational states tend to be spaced by really tiny amounts of energy. Vibrational tend to be 10 or 100 times larger. And let's try this out with carbon monoxide. Here are some numbers on carbon monoxide. People went in and looked at vibrational states. And they looked at the transition between V equals 0 and V equals 1. Okay, so if I look at the photons between 0 and 1, how's that going to be different from looking between 1 and 2? Oh, they're the same. Okay, was that true in rotation? No. But in vibration it is. What I've got in vibration is equally spaced quantum states. So what we can say here is that the energy, let me write this down. The wavelength observed for these vibrational transitions in carbon monoxide is 4.67 micrometers. Hey, that's almost the same thing as 2.61 millimeters, or is it? No. What size is that? It's a lot smaller, right? It's smaller by, what, factor of 500 or something? This would be how many microns? Oh, actually, maybe, yeah, this would be like 2,610 micrometers, and that is 4. Okay, so what can we say about the energies of the photons coming out? Yeah, it's like hundreds of times more energy, right? That's a lot more energy. If we do look at the energies here, how am I going to get the energy of this photon? hc over wavelength. And when I do that, I ended up with 0.266 eV. Yeah, these photons coming from rotational transition, they were tiny, right? These rotational states were spaced very, very close to each other. And the vibrational states are fairly spaced out. All right, you guys ready for the Physics 4B question of the day? Thermodynamics. a container of air at a temperature of 300 Kelvin, kind of room temperature, how much energy is in those molecules? How do we calculate that? Let's see. There was like a 5/2 nRT formula. Is air monatomic or diatomic? 99% diatomic, right? 99% N2 and O2. So I think of air as almost entirely diatomic. What we had said there was for diatomic gases, the internal energy was 5/2 nR delta T. What was our argument for the 5/2 value?
That it was something like rotational vibration.
That's right. What we said was that translational energies, molecule for molecule, translational energies on average are 3/2 kT. How much energy do we get from rotation? This we said was 2/2 kT, and then we also wrote down vibration, and that was another 2. Well, if I got 3/2 and 2/2 and 2 more halves, shouldn't that be 7/2?
That's only metal, right?
No, I mean this is for diatomic gases. Why is it that we only included translation and rotational energies, but we left off the vibration? It was, the temperature was too low. We said that at temperatures like hundreds of Kelvin, where are all the molecules in terms of their quantum states? Everybody's stuck in the ground state. And you have to get up to thousands of kelvins before the molecules can jump up to these excited vibrational states. Okay, so there's a little bit of quantum that they threw in right there when they said something like the vibrational states aren't populated yet, the temperature's too low. Okay. But at 300 Kelvin, are we populating a bunch of different rotational states? Absolutely. At 300 Kelvin, not a big deal to come up with this much energy to bump the molecules into higher states, but that's a fair amount of energy. Okay. So collisions between molecules and such are not going to be high enough to push these molecules into excited states. So yeah, that was the physics 4B quiz for today. All right. Oh, we got to get back to this molecule, huh? So this is the energy of the photon. You know, I think what I would like to calculate this time is what's the bond stiffness in carbon monoxide? Compared with other chemical bonds, we do expect carbon monoxide to have a relatively high bond stiffness or relatively low. Or you're wondering what the heck bond stiffness would be. And bond stiffness,
that energy that's released in the break.
well, it's kind of how stiff the bond is. And by stiff we mean that
Stability of
the nuclei can't shift back and forth very much. They're locked into place pretty well if the K value is high. If the K value is not high, it means the nuclei are able to move back and forth more readily. Carbon monoxide, it's made out of two relatively small atoms, and it's a triple bond. So we expect a really high K value. Yeah, that's a recipe for really high Ks. So let's see what a K value would be in a molecule that has, you know, probably one of the stiffest chemical bonds around. Yeah.
Is the stiffness related to bond energy? You know that.
Not necessarily. So bond energy is, if we go back to that parabola, let's go back to that energy diagram we had. Bond energy is what? How deep is the, okay, so bond energy is here. How deep is this? K is related to how narrow this is. So if this is relatively narrow, that's a large K value. K will make this, the potential energy is going to look like this, 1/2 K x squared. If I got a larger K value, it's going to give me a tighter parabola. Okay. And that says when it vibrates back and forth, it will have a narrower range of internuclear distances. Okay. So I could have something that's relatively deep and relatively narrow, or I could have something that's deep, a large bond energy, and I could have something that's much broader.
Okay.
And if you go through the periodic table, the atoms get bigger, the electron distributions get bigger, and the nuclei are able to shift back and forth, usually more. Okay. All right. I'm going to get a K value from this data. How am I going to do that? And I guess it's this, right? We already have the energy of the photon. That should be able to, we should be able to get omega from that, right? So we're going to say that the energy of the photon is equal to h bar omega. And that will give me an omega value. And the omega value I got here was 4.05 10 to the 14th radians per second. And then K should come as mu omega squared. And what was mu? Did we calculate that on Tuesday? We did, right? Mu was equal to M1, M2, M1 plus M2. Now, on all these calculations, definitely practice these. You know, the examples that we looked at here on Tuesday and the one today, go back over these. Make sure that you can keep track of all the units all the way through. The formulas are a little deceptive. You look at them and you go, yeah, it's just some, it's a plug-in, right? But the units often will make something go wrong. And let's face it, if you miss a factor of Planck's constant, how wrong is your number going to be? And it's going to be off by 10 to the 34th, which doesn't look good, right? If you say energy spacing over here is 10 to the 34th EV instead of 1, that's quite a ways off, all right? So pay very close attention to units all the way through. How did we get the reduced mass for carbon monoxide? Yeah, we took, well, you can't use, well,
You use the common isotopes.
you have to use isotopes. Yeah, you can use common isotopes. So rather than use, so for example, let's say our diatomic molecule was HCl. What should I use for the mass number for HCl? Because I'm looking at chlorine over here, and it says chlorine is 35.5. Are there any atoms of chlorine, are there any nuclei of chlorine with a mass of 35.5? No, because there's not any one made out of 35.5 protons and neutrons. That's averaged over 2 common isotopes. So I would either have to use the 35 number, or the other isotope is 37. So not a problem, I would provide that, or if it's not there, ask. And the most common isotope of oxygen would be 16. So if we go with the common isotopes, so you want to go with the integer numbers, you don't want to use the periodic table. The periodic table is averaging over different isotopes. Integer numbers are the reliable ones here. All right, I'm sure we have that number here somewhere ready to go. Very good. Okay, am I ready to plug the, and that's atomic mass units, right? Atomic mass units, am I ready to plug that into my formula?
No.
No, because I want to get this into kilograms, right? I need to get this into kilograms before I can do that, so let's do the conversion. And what did it work out to be in kilograms? 1.14, 10 to the minus 26. 1.14, 10 to the minus 26 kilograms. That's the number that I want to use. So 1.14, 10 to the minus 26 kilograms. And what am I going to put in for, put in omega, I guess, right? 4.05, 10 to the 14th. Do I have to do anything with the units on that one? No, that's in standard units, right? The radians per second look good. So what do I get for K? And first of all, what are the units going to be? Yeah, kilograms per second squared, and the radians will just drop out. Kilograms per second squared are the same thing as newtons per meter. And I think that's what we used back in 4A. I'm going to stick with that. and say the K is going to come out in newtons per meter. And when I run these numbers, okay, would you expect these numbers would be the same as like a macroscopic spring? Are the CO bonds going to be as stiff as a spring on my car? Possibly, right? Because it's a scaling issue. It's like, well, they're so tiny, you know, how rigid are they scaled down to the size of atoms and molecules? And typically these do come out, they come out in the hundreds or thousands. This one came out at, so they are kind of comparable to some fairly stiff, this one came out at 1870. So almost 2,000 newtons per meter. So yeah, we can just use standard units on these, right? Newtons, meters. That's a pretty stiff spring. From mu into kilograms, from AMU. Yeah, so what we said was the way that atomic mass units are defined, 1 gram is Avogadro's number of atomic mass units. And atomic mass units, we're just going to abbreviate as U. Okay? And so 1 kilogram would be 1,000 of those. And if I flip that around, this is the one that shows up in the books. 1.66. It's actually 1.66, right? Is it 7? I wrote 7 on Tuesday. I think it's wrong. I think it's 6. I mean, it's got to be. The 7 is the mass of a proton. I think that's it, and I think it's in the front cover of the book. So. Yeah, 1.66, 10 to the minus 27. Yeah, on Tuesday I put the mass of the proton. All right. Now there's one other thing that we could calculate here. Let's see if we get our molecule all figured out. So looking at rotational energies allowed us to calculate bond length. That was kind of interesting. And now what we're saying is that looking at vibrational